So thank you very much for having me. It's great to meet you all. I think I've spoken with most of you by this point. So the point of this talk is, by the end of it, I want to get you to do something weird with Git, like doing weird stuff with Git. This is what I'm trying to convince you to do. Or not really, but hopefully it's going to be exciting enough for you to kind of go and figure out more. So just very quickly, my name is Kiril, and I'm a co-founder and CTO of a company called GitButler. And I've been coding since 2004. Jesus, that makes me feel old. And I've been hacking on version control stuff since 2020. I really like version control. I really like Git. Let's go over this. So the outline of this talk is something like this. So it's going to be about 20 minutes. I want to tell you why operating Git programmatically is why you want to operate Git in a programmatic way. Also, afterwards, what makes hacking on a Git or with Git a pain in the ass. I can spend the entire talk on this, but I'll try not to. And then I'll give you an overview of kind of how you can do that, what libraries, what tools are out there. Then I'm going to talk about Gitoxide, which is one such library. And then at the end, I will show you some cool shit that you can do with Git. Some examples. This will be a live demo, so let's get there. Just want to say you're welcome to stop me and ask questions along the way. Please feel free to do so. I enjoy it. So why would you want to do this? Why do you want to do Git stuff in a script or in a program? So you're either doing some developer tooling like package manager, if you are Cargo, if you are NPM, or if you are an IDE integration, some kind of VS Code plugin or VS Code thing, or if you're doing infrastructure as code and then you're pulling, code from a repository, you want to programmatically trigger Git operations. And also, if you want to build various automations in your workflow of any kind, if you want to somehow manage generated code, if you're a GitHub or one of those forges, and if you have people collaborating or you want to facilitate collaboration, you may want to do this. So Git is great, but here's what makes hacking on Git a pain in the ass. Firstly, why is it great? So I'm not going to explain the data model in detail, but in Git, you have something called object database or ODB, and everything there is content addressable. So you have a hash of the object and you address it through that hash. And the type of objects that you store, not all, this is not exhaustive, but you store blobs. In Git terminology, a blob is just the content of a file, just the bytes, Trees, when we say trees in Git, it sounds very, very fancy. It's actually just file trees, right? And then in a file tree, when you reach a file, you then point to a blob, right? Like that's how it's structured. And then you have commits, like we've all heard of Git commits. What a commit is it's essentially pointing to a tree, right? So if you inspect the internals of a commit, you can run the command git catfile-p on a commit hash, and you'll see kind of which tree it's pointing to, and then go to the tree. And you can actually do this recursively. So you get a tree, you can look into the subtrees, and you can find the blob. That's how the data structure is set up. Everything is immutable. So when you create an object, it's the object, and if you want something else, it's essentially create a new object. But it's efficient because it does deltas and stuff. Then you have references. In Git references, that's what the branch is. And you're saying, this is what a branch is. It's a pointer to a commit. And then the commits form a graph because a commit points to one or multiple parents. And then you have an index, which is something. Like, let's not talk about the Git index. Now, this is the data model, and it's wonderful, and it is very flexible, and it's very performant, stable, fantastic. Git is absolutely brilliant. What's really rough is the APIs of, hello there, welcome. So you have APIs in Git that can be considered rigid, and what I mean by this is if you want to change something in your kind of Git history, you can't just do that, right? Like, because things are immutable, so you are rewriting history, and the APIs for doing that are a little bit, you have to create a new object, it needs to be linked up into the system one way or another. Also, it's kind of hard to put custom stuff, right? Like, if you want to save something about a commit, where do you put it? How do you do it, right? Like, what you can do, so there are headers, and you can save headers, but if you have other clients that do rebasing, like if you rebase at your forge, let's say GitHub, they may lose headers. So it's tricky. And then you have platform-specific stuff. Have you guys heard of Windows, the operating system? I know. We're all Mac and Linux users here, but on Windows, well, you can have files and file paths that are not UTF-8 serializable, and there's like a lot of subtlety, and you can't have com1 as a file name, because everything is tied to the file system in how Git works. You have a lot of specific stuff. And then you have garbage collection. Like I talked about the object store here, things can get GC'd. And they don't get GC'd if they're referenced through a reference or branch, but otherwise things can get GC'd. So if you want to do crazy stuff with Git, that's something to be mindful of. And also, this is not a negative point, but the Git is wonderful and stable, and that's why it's a critical piece of infrastructure, but also it's very backwards compatible and moves very slowly. And then there is stuff like Git LFS, there is submodules. Who in the audience loves submodules? There are people who love submodules, and they're useful. I don't find personally submodules useful for me, but you have custom diff drivers. You can ask it, diff me this zipped file, and it can give you something like useful, human readable. If Git alternates, if you want to share this ODB between repositories, there is this list of quirks and weird behavior is very long. So in a nutshell, you need a library. You need something so you can't just read the reference with the file and just modify. You can't do that. You need a library. You need something that implements all the Git behavior. So I'm going to give you briefly an overview of the Git low levels libraries that are out there, like a landscape lay of the land, so that you know if you want to do cool shit with Git, what can you pick up and use? So the Git and the library of it is called libgit.a. This is kind of the de facto standard, and this is what the wonderful kind of folks in the core maintainer group implement. So the tricky thing there is that this library was never written for library usage, because the function signatures are not set up for it. It returns in various places, or like exits the program. You just can't. So that's why there is something called libgit2. Libgit2 is a more modern kind of take on libgit, and it's mature, and it has bindings for most languages. So if you're using Python or C# or Ruby or any of those languages, it most likely binds to libgit2. There is a Rust crate called git2, and it binds to this, kind of creates Rust types. You can use it. It's for foreign function interface stuff, so that comes with some quirks on the Rust side. And then there is JGit. So if you wish, I love Git, but I really want my Git on the JVM. Who wants Git on the JVM here? Well, if you do, JGit is for you. That's actually maintained mainly for Garrett, the code review and hosting system. And there's GoGit, which is slightly smaller. It's a Forge focus, like it's focused, I think, GitLab, we're using this or maintaining this. Don't quote me on this, I may be getting it wrong. And then finally, there is this library called Gitoxide, and I'm gonna sell you on Gitoxide in this talk. So Gitoxide is a modern Rust implementation that is very performant, and it's what it does is very stable and robust, right? Like the project is really focused on behaving as Git would, right? So if you want programmatic access to Git data structures, that's what you would use. All right. So I have a slide here which visualizes. By the way, I've taken this slide from or this image from the slides of Byron, who is actually the main guy behind Gitoxide. He gave a talk about this 2 years ago. So what you're seeing here is the lines of code of the different kind of Git implementations. In the background, every pixel is a line of code in the respective code base. So in the background is the main Git project. So all of the area under kind of the picture. This is JGit, fairly large project. It has existed for a long time. It's in Java. You have GoGit, and this is Gitoxide as of 2024. Right? Like it's not the biggest. It's not trivial either. All right, we've made it this far. So Gitoxide, the elevator pitch, modern, fast, performant. I'm not going to say it's written in Rust, but it's written in Rust. It's a Rust meetup, so it's actually nice for consumption in Rust context. So you can find it on this URL, Gitoxide Lab/Gitoxide. It's fully compatible with the data model. So if you're using Gitoxide, writing, reading this ODB object database stuff, it will just work, right? Like it's fully compliant. It is highly performant because of the parallelism that you can do with Rust. I would love to hear somebody in the audience if you're really good at parallel Rust, but I know it's kind of one of the tricks up its sleeve. It's also safe by default, and you can do cool stuff, like you can do stuff in memory. You can do things in a transactional way. And who uses Gitoxide? Cargo uses Gitoxide, not for everything because it's not fully kind of complete, feature complete, but JJ, has anybody heard of JJ? Right. So JJ, I think they have their own implementation for stuff, but they use or used to use Gitoxide. There's Sapling. Anybody know what Sapling is? This is the version control from Meta / Facebook, and I think, or last time I checked, there was usage of Gitoxide there, and GitButler uses Gitoxide. It's actually kind of really underpinned by Gitoxide. Okay, so I'm gonna show you a little bit of code, just a tiny little bit of code. Just to give you a taste, because it's a Rust meetup. I just want to show you what it looks like to use the thing. So in the first example, this is how one would update a reference. And what's interesting here is, okay, you have some interface, you say .reference, and then you're providing a new value. But what's interesting is you're specifying what my previous value was, and then the system would kind of check, is the assumption that the color of this, does it hold? And if it does hold, it will perform the operation. If not, if something happened, then it's like, okay, we'll abort out of this. So the Gitoxide crate has a lot of kind of very detailed APIs that can do things in a super granular way. Here's an example. It's a little bit smaller, but here's an example of doing something in memory. So I think the interesting part is that so here we are creating a tree, and we're creating a tree out in a in-memory version of the repository, which means you can discard the result, right? Like you can do stuff, discard the result and be performant and or commit it only, or like write it to disk only if it makes sense. So yeah, that's kind of useful if you're trying to build kind of applications that use these structures in a way that is yeah, interesting. So we've made it to the demo portion of this presentation. So I'll show you three cool things you can do with the capability of programmatically accessing Git, right? Like, so first I'll show you like a command called absorb, or like an imagined command called absorb. It doesn't exist in Git. It exists in Jiu-Jitsu or other tools, but it's not a native Git thing. And I'll show you something about editing history, like rebase-i. Who here does interactive rebasing of Git? Okay, right? Like you do interactive rebasing because you want to change the history. And rebase-i, it's a script, right? Like you're running a step after step and you're saying, this step, pause, I'm going to edit some stuff, etc. But what if you can manipulate more directly the data structures and then you write it out? And I will finally show you an example of an undo. All right. So let me set this up. Mostly set up. So I have my terminal here. So I'm in a repository. I'm in the Gitoxide repository, and I have nothing. So I'm going to make a change to the README. I'll just destroy it a little bit, just like this. So I'm going to run a GitButler command. Ignore the fact that it's a weird command, but I'll just use this in order to show you what we have here. So we have an unstaged file or unstaged change in readme.md. So I'm gonna say, okay, let's branch new my branch. So if I run this again, now I have a branch. So let's say I run this but absorb command. So what this did was it absorbed a change into a commit that didn't exist. So if I run status again, now I have a commit without a message. And if I make another change to this guy over here, and okay, actually I can do the following. I can run it again, and it absorbed it once more. So if I run status, I can show you by diff 40. I'm just using the identifiers to run various commands. So here's what I have in this commit. So I can keep absorbing stuff into this commit or multiple commits. But what if I had changes that, let's actually make a change in a new file, ABC. I'll just make some stuff up. So, sorry. If I run status, so I have an unstaged or uncommitted, like untracked file ABC, and I have my my commit from before. So I'll make one more change to the README, like this. So if I want to make two separate commits, let's say I want to make a commit for. Actually, this is getting too long. Is it too detailed into the product? I can tweak it a little bit. But essentially, this command is going to absorb things into the relevant command. If I have multiple, or into the relevant commit, if I have multiple commits, this stuff will go into the right one.
Is that just based on the path?
It's based off of the dependency. So if I have a change, okay, actually, let me show you this. I should have prepared this ahead of time. I'll commit this one. Like this. So now I have two commits, and if I make a change So I can run status with files, so I can see the files that go into the different commits. So here I have ABC and I have the README, and if I say about diff I0, I have these diffs here. So if I edit the README again, like so, I have a change here, and there's this little lock icon and saying, okay, this is actually depending on this commit over here. So if I run the absorb, it's going to, well, absorb it into the relevant commit. So if I run this status file command, I'll say, okay, the change here in I0, diff I0, now I have the extra stuff that I typed in there. So it's kind of log-based. Or dependency-based. So this is the absorb idea. This does not exist in Git, right? Like you make it up and you essentially build it off of the primitives. Here's another thing that you can, in theory, do. So I mentioned absorb. I'll mention editing the history. Like I have my but status. So I have this commit over here, 15f something something. It has no commit message. So I can say reword and then type 15, say my commit. So if I run this again, yeah, it now has a commit message. And ta-da, we edited history. Yeah. So I'll show you something that is actually my favorite part. So if there's one thing to be awake for, it's this one. So, you know, if I want to move this, okay, so let's say I submit this for review, and some of you guys is my reviewer, and you tell me, hey, I love your PR, but you've dumped everything into this my commit, the D1 something something commit. And you're like, can you move the ABC file to to the subsequent commit? I'm like, sure. Now I have to run interactive rebase. How would you do it? You would run interactive rebase. You will stop at this commit, kind of edit or remove the thing, put it back, and so on. How you do this with this tool is you say, so I actually can run this command rub, and I can take this J0. So I'm taking the identifier here, and I'm picking the identifier of this commit. So I say 03. Right. So if I run this, ta-da! I've moved a tree and blob from one commit to the other. And if I say I want to, if I want to create a stack, or like what is a stack? People talk about stacking branches. This is actually simpler, or it doesn't have to be complicated. So a branch. Let me just remind myself. Okay, so I can pass A. So if I say dash A, my dash. Okay. So now I have a branch here. And what if I want to move this commit 8F to be above it, right? So if I want this guy to go up here, I'll just say, but rub 8F. I'm surprised nobody has commented on the naming structure that we're using here. KV. So okay, essentially the idea is you're combining objects. I'm saying I'm combining this source to this target, and it's like get the result, get the outcome. What do you expect to happen out of this? So there we go. We move the commit from one branch to the other. That's the kind of stuff that you can do. This is trivial to do if you have that intricate control over the data structures. I think I'm gonna not get any deeper in this. The last thing I wanted to show you is like undo. You can implement stuff like undo, like right. So I moved back. Like, and how does undo work? You can to implement undo, you have to do some intricate stuff. You have to have something like an oplog that stores each state. So this is kind of every operation that I've performed thus far. Yeah, it's the oplog. So this was hopefully short enough of a demo. Did not really prepare it too much ahead of time. I just want to get you excited about what you can do, because the sky is the limit, honestly. Like, you can do so much. This is a bunch of links to various stuff. But mainly, hopefully you find Gitoxide exciting. You can check it out. You can see. I know some of you in the audience work on infrastructure as code and stuff like that. Think about what the cool stuff you can do. The demo that I showed you, this is part of GitButler, and GitButler is a layer above GitHub. It's a client and an SDK and a CLI. It has a GUI as well that can allow you to do some magic operations like that. And with that, let's do, if you guys have questions or want me to explain something. Yes?
How does your oplog work? Is that like using the ref log? Is that a separate database that you're storing somewhere?
That's a brilliant question. I love it. So the way we do the oplog is we create, so I mentioned Git trees, so we create our own custom Git tree. So that means somewhere in the application we're saying, take the working directory, that's one tree. Then we put some other stuff, which is metadata related to the commits, related to the references, related to all the metadata that makes up the state. We store that in a custom tree, and we create a commit. And we do this over and over again every time we perform an operation. But there is one but. If you do not have a reference pointing to that commit, you get garbage collected. Right? Like, after some time, the commit is poof, gone, and then you can't do revert anymore. But you really want to use that system, because this system is going to be very efficient, and you have the whole the storage is very nice and incremental like this. So what do? You create a reference. But if you create a reference, then when you type git log --o, you see a bunch of kind of unrelated stuff. We don't want that. So we have like a hack through the reflog. So we create a reflog entry where we pretend that the thing started off from that branch, and we keep rewriting the reflog entry directly. That's actually very, very hacky. But that's one way of avoiding getting garbage collected and also not showing up in the kind of new stuff. If you want to know more about this, I can point you. So you can find it here on this URL, but if you want to find exactly the solution, I can point it to you.
Thank you.
Mm-hmm. Any questions or? Yes?
So you're telling me Git does garbage collection?
Yes.
My orphaned commits don't stick around forever? Or?
Correct. So they also call it prune, and by default it's 2 weeks, and you can tweak it, you can configure it. The way it does it is there is no background process, so when you run commands, it will occasionally decide to prune stuff. So it's a wonderful thing. It's a wonderful structure, and it has even the CLI. It can do a lot of stuff, like the application itself. But I think the data structures themselves are really fascinating. Tom.
So you mentioned the git command as like putting your command in the background. Is that something you had to take over as well as Gitoxide, or you just hope someone's going to accidentally run git status and all that?
Which command?
Like the git GC, like the garbage collection.
Yeah, so we prevent garbage collection through this reflog hack. So we have a reference.
No, but like, do you do garbage collection for other stuff? Like, as in, because if I use GitButler,
yeah,
I don't use the git command, and then I don't have the automatic garbage collection, right?
It will still garbage collect, because under the hood, GitButler will run. So for fetching and pushing, we use we fork exec. So I was saying how we don't have to fork exec, but actually the network stuff is really, really specific. You can set it up in so many different ways. So yeah, for that, yeah.
There is like a background
Yeah.
Are you coordinating with that at all, or are you just?
Not at all. No, that's something for kind of large repositories. Yeah.
Are you saying orphan commits in the ref log get removed?
I mean, if they're not referenced anywhere.
Because I've done analysis on repos to try to find orphan commits, and I find stuff that goes back 10 years.
And my presumption there, and I'm kind of without understanding the case, but there ought to be some kind of reference pointing to it one way or another. Or there may be somehow one of the parents on the merge commit and it was referenced somewhere. Well, that would be my presumption, but I may be missing some nuance.
I'm trying to understand what you're talking about with the garbage collection. What exactly gets removed? Because I've done these types of processes before as like sort of code archaeology or finding code, and it's worked really well. Multiple times. And the whole case like again runs from I see from Max and I see all those things that go on there.
Yeah.
So I'm wondering, is it maybe a setting?
You can disable the GC if you wish, or you can change the frequency of how often it runs. But what gets GC'd is the stuff in the object database, and that's trees or file trees. That's blobs and commits, and a commit would be pointing to a tree, pointing to a blob. And then if you have objects that are not reachable from any reference, and reference are kind of separate, in that case, they should get garbage collected.
Is my local copy the same as, let's say, your local copy? Or do if it goes to like .git and says it's AD, AC, all these like files. I'm saying that if I go like a CK sound or like an MD5, some of all those files, do they do the same when you're online? Or do they like get reconstituted for that purpose?
So the ODB, or like the objects that we're talking about, they would be the same, right? Like if we, this is kind of part of the whole integrities of the. So you would have the commit, which would be pointing to a tree, and.
I think it was data integrity layer line. I was buying it. That's right.
Yeah, we can talk about it later. So, thank you so much.
Great, cool. So this is part of a project I was working on. I've been working on it for about a year. It's something called Autoschematic. Has anybody? Mike?
I just can't hear you here.
Okay, sorry. Okay. Just a show of hands, who here has used Terraform? Okay, wow, okay, cool. Who here knows what goes on under the hood, like when you run a Docker container, let's say? Okay, cool, awesome, great. Well, you can all leave, so it's fine. Very good. So this is kind of, this is all sort of background context. Basically, before we start, when we say a Linux sandbox, we mean some way of isolating, like running processes on a Linux host from one another, so that they can't modify each other's files or access each other's secrets on some level, or even just view each other's like running environment, for example. And when we say plain Rust, we mean like you can't just spin up a Docker container. That's cheating, right? You want to actually do something in Rust meaningful. So here's some technical background. Autoschematic is a tool. It's kind of like Terraform. It's designed very differently from Terraform. I'll show it off later. But it does have the same kind of core. The architecture is something like plugin based. Has Terraform has providers. I have something I call connectors. Something like this. Each connector kind of manages a certain type of resource, just like a Terraform provider. And we spin up connectors just as like plain processes, plain Rust binaries. They talk over a Unix domain socket over, anyone use tarPC? Anyone heard of tarPC? It's really cool. It's like, you ever use gRPC? It's like gRPC, except you don't write proto files. It just takes it directly from like a Rust trait. It's awesome. It's really great. That's why I support 2, because tarpc is just great for like iterating really fast, and grpc is, in case you ever want to run like JavaScript connectors or something silly like that. So we have this scheme here where we have a parent process, which is Autoschematic, and then we have these child processes, which are like connectors or providers. And in implementing what I was calling sealed secrets, sort of like SOPs, I came into the problem where if you implement sealed secrets, you have this problem where connectors can always read each other's secrets. You don't have any isolation between them if they're all running on the same host, you see. So I got into this technical problem. I kind of nerd sniped myself a little bit in implementing like very basic sandboxing on like a Linux, ideally a server host. So yes, as we see, if you just run a plain Linux process, you can read anything. You can read your SSH private key or something like that. And we need to kind of lock down what a connector sees in terms of what its actual file system and environment is. So we do have a mechanism in the Linux kernel called namespaces. These were introduced in about 2013 in Linux 3.8. And what a namespace does is it allows processes to have different viewpoints of what were previously like global kernel resources. For example, the mount table describes every mount that you have in the system. When you run the mount command, it'll list like, slash, some devsda at slash, devsdb at whatever. And that's the mount table. So with the namespaces, you can have 2 processes that have a different viewpoint of the mount table, or different user IDs, or they can be in different times. They can have different system times, or they can have different host names. So these are the Linux namespaces that we provide. This is very dry. I'm going to have a few really dry slides, so just bear with me, okay? We can have different network namespaces, IPC namespaces, C groups. This all sounds probably pretty similar to Docker. If you're these are all the sort of the kind of core primitives that Docker, for example, uses to implement containerization. So you think it's pretty easy. Okay, all we have to do is clone a process, run the clone syscall, and add some flags. Great, okay, cool. But here, what does that actually get us? As you can see with the comment I've written, it starts a new process in a new namespace, but that process actually inherits a copy of the previous mount table and a copy of all the open file descriptors. So really, we're not actually getting anything by this. It gets a split copy. It doesn't share state. It gets a copy, right? So this is cool. Actually, you can see like I actually allocate a process stack, which I haven't done since I did like operating systems in C for college. Anyway, we set up the stack and environments and all this stuff, and then we enter a new process at the clone call there when we pass our flags. So yeah, even though we're in a new namespace, we've received copies of all this stuff. So we're not actually getting anything. If you ran a connector that was just like a debug shell, which I have, you'll see like, oh, it's just the same. But if you type, because we created a new user namespace, if you type who am I, it says nobody. And your user ID is actually like the overflow ID. It's like 65534 or something like that. So because you're in a user namespace, you're in this like weird interim state, right? I'll touch back on that. So to start with, the first thing to lock down is the file system. We want to have a different mount table, so we want to have a different view of the file systems. And so we'll start. We will say we want to create like a root file system. This is pretty easy. I haven't written out the script for this here, but it's just a straightforward script. We take a minimal Debian image. We just apt install CA certificates, and we have a name server just to Cloudflare DNS to resolve DNS. So because we're not creating a new network namespace, our new process will share the host namespace. The host network. But even because you have a new root file system, you have to put that in. The CA certificates and the DNS stuff. That's actually on the file system, not in the kernel. So we get a squashfs image, and that'll be kind of our root, like, I guess that's part of a Docker container is the rootfs and layers on top of a rootfs. We'll just pass around regular squashfs images, right? And the goal is that like the sandbox process will see that as its root. Somehow we have to set this up. And we could do like, eventually we'll do a pivot root, which is sort of like a CH root, but it actually swaps two mount points. I'll get around to that. And not only do we want to have a root file system, we also want to selectively bind stuff from the host into the file system, into the new kind of view of the file system. Like we want to have like /secret, that's where we'll put our secrets, our sealed secrets, /repo, that's actually a Git repo. We do lots of Git operations as kind of infrastructure as code thing, which is why it's relevant. And also that folder where we store our sockets, it must have that folder as well. Otherwise, there's no way to communicate with it. So, like, we've got to achieve this somehow. We've got to set up this new mount table, and we can do this with bind mounts, right? We can using like a mount -- bind or the syscall mount with the bind flag on it. It'll create a bind mount, so it'll actually almost in the new mount table, it'll almost be able to take a direct view of that folder. You're just kind of mapping one folder onto another. Anybody ever used Plan 9? Anybody ever, really? Anybody heard of Plan 9? Okay, cool. Yeah. Should be more people. You guys need to know about Plan 9, man. It's really cool. It's like the foundation of everything modern in Linux. It's awesome. And so, in addition to the bind mounts, we also can use overlay.fs and create like an in-memory kind of temporary, like ephemeral scratch over the read-only bind. That's cool. But binding anything requires root. Or sorry, mounting anything requires root. You can't run the mount command if you're not root. And you're probably going to say like, oh, aren't you going to use fuse or something like that? But that's a whole other can of worms. You have to mount like loopback devices for this. It's not really going to work that well. So here's the real trick. This is actually the trick. Even though we run a process without any privileges. We don't do like, because you would never do sudo Terraform. That would be terrible. That would be like insanity. We just run an unprivileged process. But once we create a new user namespace, we have in the Linux kernel like terminology, we have capsysadmin, we're an admin user inside that namespace. So there's some more really dry stuff about like procfs mappings here. If you really want to know, I can dig into it at some point. But as long as we define a mapping that says this host user that we're running as, sorry, let me back up. We define a mapping that says root inside this user namespace should correspond to the regular host user outside the namespace. Trivial thing, but it underpins everything. So some really dry code again. We're just writing these entries to proc. This really is just plain Rust. There's no helper libraries. There's Nix, which is a great library, which provides a safe interface to lots of like libc and Linux kernel interfaces. It's really good. That's like the underpinning thing here. But apart from the Nix crate, it's just plain old Rust, right? So we're inside this namespace. We set up our UID map. We set groups to deny. We set up our GID map. And then we do like set UID 0. So here we become root inside this namespace, inside this new user namespace. And it works. Even though you're an unprivileged user, you're root inside this namespace. And outside the namespace, you're just the ordinary user again. So here, yeah, you're before the clone, we're user 1000. After the clone, we're the overflow user. We're nobody. If you type who am I, you get nobody, and you're this overflow 65534 user. And then after you set res UID to 0, now you're root. Now you're root inside the sandbox namespace here. Cool. So now all we have to do is set things up. Before we pass control to the connector process, we're just going to set things up set the environment up. So we do things like we mount temp. We mount a new tempfs because we've lost that. We mount a new tempfs for our sockets to live in. Or sorry, we bind the sockets from the host, the folder where the sockets are stored, so we can communicate with the host, or vice versa. Now we do the pivot root. As you say, here's some real fuckery. Pivot root is slightly like CH root, except it swaps two mount points. We pivot root, we mount the new procfs, and now we unmount our old root. And now, in theory, there's no mount table entry that references the old host file system. So now we're in a much better spot. We're getting somewhere. We do some clever stuff where we can we pass through like standard I/O to those files and kind of almost take two like pipes and plug them into standard I/O so the host can read the standard I/O from the child process, and then we close all the existing file descriptors that it might have inherited from the old process. So if it has any secrets open or anything like that, we prevent the child process from just being like able to read it from whatever open file descriptors there are. And this is just included for completion. We set up an environment and we do exec.pe. We pass control to our connector. There's nothing really here except for including for completion's sake. So how do we know this actually works? How do we know that this is a real sandbox, right? We have to test this somehow, and we're going to create like an evil connector. It'll try and do something really evil, and this is the most evil thing I can imagine. It's going to read my SSH private key folder, as well as what it thinks the old root might be if it's still mounted. And then it's going to dump the contents of these to this giant monitor in front of you all with a recording camera. So let's try this out. Where did I put this here? Ah, yes. So just for reference, here's our main like root config. We only define one connector, and it's this evil connector that I'm spawning in the same directory here. That's our only config we have. I'll show you some more Autoschematic config later, but okay. Here I'm setting some environment variables to enable the sandboxing and point to a mounted rootfs that we have. That's going to run this evil connector, and if the sandbox doesn't work, you're all going to see my SSH private key, and it's going to be really embarrassing, and my pants are probably going to fall down or something. But let's try it. No, nothing. It can't read it. I have a log proc self status just to see the permissions here, and you can see that even though it does have root in this thing, it has root, but it's only root inside the namespace. We've unmounted everything, and so it doesn't print any of the SSH keys or anything to the console there because it can't. It doesn't see anything. And basically, the crux of my talk here was just that Rust makes this kind of experience a lot easier, just in terms of. Let me actually get back to presenting here. In particular, the Nix crate, because we have this safe interface to stuff like libc and like kernel level APIs, and also we have stuff like ownedfd, which prevents you from doing things like dropping stale FDs, file descriptors that is, and kind of enforces certain like semantics around file descriptors that were otherwise just like huge footguns in C, for example. And yeah, I mean it's kind of more of a Rust adjacent talk in a Rust project with Rust implementation, but that's my conclusion, I guess, is that Rust really is really effective for stuff like this, and it's kind of a joy to write cool, interesting system software with this. The error handling story is, for one thing, is a lot better, and it just feels a lot nicer. It's a lot more robust, I think. I think you'll agree. Cool. Are there any questions? Yeah.
So you mentioned when you do a clone, it's essentially like a fork, right?
The what, sorry?
Like when you do a clone.
Yeah, it's just like a clone.
We mentioned that it keeps the file description and all of that. Like,
yeah.
Well, what did you mention about like that? Those being dropped automatically?
What's that, sorry?
Are they dropped automatically?
Oh.
What did you say about?
Oh, about ownedfd. Oh, you know what?
Only a specific file descriptor that dropped automatically?
It keeps a copy of the file descriptor table. I might have misspoken about ownedfd. Ownedfd enforces some kind of semantics around a raw file descriptor, but I might have double check on that. Yeah.
So, how did you find that this compares to like FireJail or other sort of existing products in the space? Is it faster to integrate? Did it add new features that you could get with other?
If I'm remembering rightly, I think FireJail was released about the time when I was writing this, so it wasn't even on my radar. I think I was writing this talk and then I saw FireJail. I was like, that would have been really useful, man. That would have saved me a lot of time. Let me just check that actually. FireJail. Oh no, something is something completely different. Yes, on this front, I'm not sure. I don't know.
Totally unrelated question. So for Autoschematic, are your plugins mostly written also in Rust, or is it like a...
Yeah. But I added the gRPC just so I could like have a proof of concept like a JavaScript one and a Python one, and they work pretty well. Yeah. No.
So the connector you were running there was, I mean, at the end of the day, it's running namespace of the UID of 0.
Yeah, you can do a setup with the sub UID file to allow it to like assume another UID after that and drop capabilities. But within the namespace, it's like caps admin within the namespace. So in theory, it could be hardened further, but it at least has. I don't know. At least I can't see any way of doing that. If anyone can crack this, like I'll buy you a beer. It'll be fun. But yeah. Cool.
So actually, one more thing.
Yeah.
We're gonna do something. This Rust meetup, we're gonna start doing something a bit different. Is that let people showcase cool stuff they built with Rust. And actually, we're gonna start with Peter.
Yeah.
And it's gonna give us like a quick demo of Autoschematic and maybe bring this whole talk to life. Again, a quick one. Peter, you have like 3.5 minutes.
Yes, no problem.
Like
okay, I'm going to try and show a non-evil connector. It's going to be much better.
That'd be cool.
Okay.
And after that, we're going to have Kiril again. He's going to show us the GitButler, and actually not just the CLI, but they have a GUI component as well that's built with Tauri.
Yes.
And he also has some strong opinions there, so I'm looking forward to hearing those. Again, also 3.5 minutes. And then if anyone wants to showcase anything that they've built, or even not something that they built, but just you discovered GitButler, and actually you want to show it and it's written in Rust, you can also come and like just show something, a cool Rust library, anything like that for like 1 minute. And you can use my computer if you need it, so just let me know and you can do that as well. Yeah. Have I stalled enough? Peter, good?
Yes. Yeah. Thank you. Perfect. Okay, cool. So we got so many hands when I asked who has used Terraform, so hopefully this all makes sense. Here we have a similar kind of concept, but I'll show you why it's different. So here we have similarly like declarative infrastructure, like infrastructure as code essentially. Oh, does anybody know Ron, the JSON kind of alternative in Rust? Yeah, this uses Ron heavily. It's actually like language independent, but lots of the connectors just use Ron because Ron is actually amazing. You can do like some types in Ron, and you can't do that in JSON easily. It's like way better. So for example, RON, like the Rusty object notation. It's really good. I've contributed a bit to it, and it's really great. Yeah. So here we have like a DNS record, like as Ron, and none of this doesn't use Terraform at all under the hood. This is all like 100% kind of from scratch, if you will. But like you have the AWS Route 53 connector, which essentially interprets this, right? And we also have it hooked up to a language server. So the VS Code extension is also running instances of connectors here. So that's how you get these like language server hints, like autocompletion and stuff. So this is cool. This is all very fine, but I forgot to open up the thing I used to generate a state drift. 1 second. So, 1 moment. This is all very fine, but we often run into the situation where we either don't have Terraform for some infrastructure that someone spun up, or the Terraform has gone out of sync. In other words, there's state drift. Maybe someone's modified something manually, like through the AWS console, and it no longer matches your code. And in working in infrastructure, this was just such a pervasive problem at like multiple clients that I wanted to start working on something that could just kind of mitigate that completely. And for example, I'll just take this, I'll just delete all the Route 53 code, all the Route 53 ISE that is, and go here. Okay, and what we could do actually is just directly import what we already have. Because resources are, if you can see the paths here, resources are actually kind of content addressed. So the layout is actually deterministic. The folder structure is deterministic, which means you can do this kind of automatic import of everything manually. We also integrate with Git. Import for demo, hard to spell. Cool. That's fine. Now let me just get on this here real quick. I meant to have this open. This is why this is just the AWS console. So for example, like if I just open up the console here, let me just, I'm just going to modify a DNS record manually. We'll introduce some state drift really quickly. I'm going to set it to something just totally stupid. You know, like.
This is how you end up with your website.
Exactly, yeah. Like, and let's go to my thing here. It was DJ that I modified. So here, this is the stale, like out of sync state. And because we have this kind of two-way state model, what I can do is I can just compare that with the remote state like this. So here we actually have the remote state compared just as a thing, because it integrates with the VS Code extension and the language server. And if we say like, oh, actually that manual change was correct, we don't want to wipe it out with our configuration, we can also just pull state like this. Yeah. So this is what I mean when I say it's like a two-way state model. The state model is kind of like push-pull, in other words, because things are content addressable like this. So yeah, I think maybe that's nearly at 3.5, but yeah, cool.
Okay, so back to demoing this. So I showed you kind of a demo with the CLI to illustrate a point, but I will now talk about GitButler proper. So actually I have some notes here. I want to show you that there is a GUI. So this thing that I showed you over here, is you can invoke GUI. No, without the GUI. There is no GUI command. And the same stuff that was rendered in the CLI, kind of you have it as a GUI application. So you have the stack branches that we had over here, and this is the uncommitted file. Yes, I do. There we go. I'm glad you asked. Yes.
What UI framework is this?
Glad you asked. So this is using Tori, which is a Rust framework. We are, in fact, considering or exploring switching away from Tori, however, mainly in order to better serve Linux users. So Tori is a little bit difficult on Linux. But yeah, so you have drag and drop operations. Like I can drag this thing into the commit from the earlier demo. I can drag this one into the commit above. Yeah, so this part. Another thing I wanted to show you very quickly is that everything that I demoed with status, we have this --JSON, so you can just get raw data, and you can. So everything that I demoed with operating with the CLI on these data structures, you can script very nicely. So it's particularly nice if you are sending it into Cloud Code or something like that. Actually, let's see what else I have. Yes, it has AI hooks, so you can set up. Okay, let's demo it here. So you can set yourself up. Yeah, so you can configure your Cloud Code or cursor to so through hooks to do certain things on the GitButler side. And this is leading me to the last feature that I wanted to, or the first in this list that I wanted to show, which is parallel branches. So this is a stack. I have my first branch or bottom branch here, the top one here. What I can do is I can have a parallel one. Why do you want to do this? Well, sometimes you have a fix that does not depend on something else. So you can have it pushed without a dependency, and you can do that with the CLI as well. You can see how it's rendered. So here we render a stack. So this is the stack that we created in the earlier demo. This is the new stack or the new branch that is independent. So if I choose to push this to the remote, actually I don't have push rights to this remote. But if I push this, I'm only pushing this commit off of the base that it's from. And this one is a stack. So when you have a stack, slightly different rules apply, because by pushing this, you're also pushing the branch underneath. That's it. That's the 3.5 on time demo. Like I did not go over. All right. Thank you.
Cool. So thank you, everyone.
Yes.
There's pizza, beverages, and you can catch both Peter and Kiril. Another round of applause, actually. So thank you again, guys. You can catch them for more questions. You can geek out about Git garbage collection as well. Everything you need. So cool. Thank you.